bases can catalyze the enolization of an aldehyde or a ketone to an enol, an aqueous solution. So I'm going to do this with an aldehyde, but be aware this could be done with a ketone. If you do it with a ketone, you can do it with a symmetrical or an asymmetrical ketone. If you do it with a symmetrical ketone, it doesn't matter which side you do it to. If it's asymmetrical, you need to worry about whether the conditions favor the kinetic product or the thermodynamic product, because you could form either enolate as your intermediate. So be aware of those conditions, whether the conditions favor kinetic or thermodynamic. I am going to do this with an aldehyde. Now, if you have an aldehyde and you actually want it to favor more of the enol in solution, you could add a base. And this base may come in the form of sodium hydroxide or potassium hydroxide. We usually do use a hydroxide, and this will be done in water. Now, this reaction is at equilibrium. I need to remind you of that it is at equilibrium. But this will help us form more of the enol in solution. So there's two things that this hydroxide really can do. It can act as a base or as a nucleophile, and it actually will do both. There is no reason why this hydroxide could not act as a nucleophile toward the carbonyl carbon and make a hydrate. It will. There's no reason why it wouldn't. So I don't want someone thinking, well, why doesn't it do that here? It does. It's in equilibrium. We're just not talking about that hydrate formation. If you want to look at that mechanism, you're welcome to go back into the aldehydes and ketones information and find that. It's happening here as well. But something else that also occurs is that these protons on the alpha carbon are semi-acidic as well. If they're on an aldehyde, the pKa for those protons is about 16 or 17-ish. If they're on a ketone, they might be 18, 19, at most maybe 20-ish. So there's an equilibrium here. Hydroxide's corresponding conjugate acid is water, which has a pKa right around 16. So it's an equilibrium that goes back and forth. I don't want you thinking it's going to remove this proton favorably. It doesn't, but it can remove it. So if hydroxide's acting as a base, not the nucleophile, you go after the proton. And as you do so, the carbon-hydrogen bond breaks and the electrons can be given to the carbon. And by doing so, you'll be able to make the enolate intermediate. I'm going to draw all the groups around the alpha carbon so that you remember exactly how many bonds you have at any given time. I find that students forget when they don't draw out all the things around that carbon sometimes. Okay, and then we've also formed water. Now, this enolate does have resonance delocalization of that negative charge onto the carbonyl oxygen. And that resonance structure there on the bottom is actually the predominant resonance structure because the negative charge is on the oxygen. But I really like using the one on the top. I like both of them. They can both be used. But be aware that these are in equilibrium, and the bottom one is the major contributor to the resonance. At this point, it would be more useful to use the bottom resonance structure, but you need to show the oxygen picking up the proton from water. So I'm going to redraw your water so you can see it a little easier. Again, you can use either resonance structure to show this. But this oxygen can come in here and remove the proton, give electrons back. Or if you want to use the one on the top, you can use this pair of electrons to form the double bond, and then use this pair of electrons to pick up the proton, give electrons to the oxygen. Doesn't matter. But when you're done, you can draw out the enol. And notice that you regenerate the base because this is a catalyst. So it needs to be reformed during the course of the reaction.